All right, so let's see if we can derive an expression for the change of entropy for the universe for a spontaneous process, but we only do it in terms of using only system terms. All right, so here's what we got. So in the last video, we talked about the change in entropy of the universe. That's equal to the change in entropy of the system plus the change in entropy of the surroundings. And this has to be greater than 0. So we said that for an exothermic process, that's going to be true. Okay. Now, what I want to do, if we're only going to use the system terms, we got to get rid of the surroundings part. Now, remember that we said that in the last video as well, that the change in entropy of the surroundings, that's going to be equal to the negative change in enthalpy of the system divided by the temperature. Okay, so what I'm going to do is let's replace the change in entropy of the surroundings with delta H system divided by T. So I'm going to rewrite this. The change in entropy of the system minus delta H of the system divided by T, and that's going to be greater than 0. All right, now what I need to do, however, since we've got the temperature in a fraction, and that's the denominator, if we multiply both sides, if we multiply this expression by T, we also have to multiply, so we get rid of that denominator, we have to multiply the change in entropy of the system times T, and we also have to do the same thing to the right hand side. Now 0 times T is still going to be 0, so we don't have to worry about that, but here's what we get. The T times the change in entropy of the system minus the change in enthalpy of the system is going to be greater than 0. All right. All right, and this is still equal. This is all equal to the change in entropy of the universe. Okay, which we also have to multiply by T. So there it is. All right. Now, I would like to get, because I would like to make that enthalpy, the enthalpy of the system, I would like to make that positive, because remember the units. The units for entropy is going to be joules per k mole. The units for the enthalpy is going to be kilojoules per mole. So that means the enthalpy value is going to be a lot bigger than the entropy. So what I'm going to do is multiply both sides of this equation. Okay, I'm going to multiply it by -1. And what that does is going to help us flip all the signs here. So we're going to get negative T delta S of the universe is equal to negative T delta S of the system plus the enthalpy of the system. Okay. Now I'm going to ignore the greater than 0 part, because that doesn't really, that's all well and good, but here's what we're at. If I rearrange the right hand side of this equation and I put the enthalpy first, okay, so the change in enthalpy of the system minus T delta S of the system, this is going to be equal to negative T delta S of the universe. Okay. What this is allowing us to do is basically say this whole thing right here, the negative T delta S of the universe, this is actually our new term G, and that stands for Gibbs Free Energy. Where G, the Gibbs Free Energy, is equal to the enthalpy, H, minus the temperature times the entropy. And so we can actually write this. This is a state function just like entropy, just like enthalpy. So that means that delta G would be equal to delta H minus T delta S. And so that's what we've done. Delta H of the system, that's delta H of the reaction. T delta S of the system, that's T delta S of the reaction. Okay? And a negative T delta S of the universe, that's your delta G. Okay? So this delta G thing, that's what we want. Okay? So the final version of this equation, I'm going to rewrite again. Delta G is equal to delta H minus T delta S. Now, what does free mean in this context? When we talk about free energy, we're talking about available energy. If I can spell available right. All right. Now, we interpreted delta G. If you guys remember way back when we talked about solutions, we interpreted delta G in 3 different scenarios. We said that delta G was greater than 0, delta G was less than 0, and then delta G was 0. Okay, so the way that we interpret it, if delta G is greater than 0, so that means it's a positive value, that means it's going to be non-spontaneous in the forward direction. Okay. If delta G is less than 0, so it's negative, that means it's going to be spontaneous in the forward direction. And if delta G is at 0, we're at equilibrium. All right, so now the next thing that we're saying is give the definition of the standard free energy of reaction with all the details. So let's see what we got going on here. So that means we're looking at delta G naught. And the way that we define delta G prime, or delta G naught, this would be the free energy change for a reaction when it occurs under standard state conditions when reactants in their standard state are converted to products in their standard state. Okay. Now it says, give the definition for the standard free energy of formation with all the details. So that term is delta G sub F. And so this is the free energy change that occurs when 1 mole of the compound is synthesized from its elements in their standard states. Okay. Now, what other state function has a parallel system? The change in enthalpy of formation. All right, so then give the useful equation for calculating the free energy change for the reactions. What that would be is delta G, standard state of the reaction, is going to be equal to the sum of all the delta G of formations of the products minus the sum of all the delta G's of formations of the reactants times their stoichiometric coefficients. All right, so we got another problem to deal with. Consider the thermal decomposition of calcium carbonate. And so this is the same reaction we've taken a look at. Part A, use the data in Appendix C to calculate the standard free energy change for this reaction at 25 degrees Celsius. Okay. So Part A, use this equation that we just talked about right here to calculate free energy. Okay, so that all we have to do is look up those values, multiply them by the stoichiometric coefficients, and we're good. Part B, will a mixture of solid calcium carbonate, solid calcium oxide, and gaseous CO2 at 1 atmosphere pressure react spontaneously to produce more calcium oxide and carbon dioxide? Okay, so we got to figure out, if we have a mixture of these three, will they react to produce more product? Okay, that's the next question. Part C, assuming that delta H and delta S are independent of temperature, estimate the temperature at which the reaction becomes spontaneous. All right, so we got 3 different things that we're looking at in this question. All right, we want to know in Part A, so let's make some notes here. We want to know delta G. We want to know the Gibbs free energy of the reaction based on all the delta GFs of the reaction. Part B, we interpret the delta G value. So based on A, based on Part A, is it plus or minus? Which way is the reaction going? Is it spontaneous or is it non-spontaneous? And then Part C, at what temperature, so we're solving for temperature, at what temperature does this become spontaneous? So it's actually kind of giving us a heads up that Part B, because of the way Part C is worded, Part B most likely is telling us that this is going to be non-spontaneous. But we need to verify this. All right. So to answer these questions, let's start with Part A first. Okay, so we have to consult an appendix of thermodynamic values in order to find the Gibbs free energies of formations of these compounds. So we need to look up the value for delta G sub F of calcium carbonate, solid, of calcium oxide, also solid, and then CO2 as a gas. Okay, so if we look up those values, the value for calcium carbonate of solid, that should be negative 1129.1 kilojoules per mole. For calcium oxide, that value should be negative 603.3 kilojoules per mole. Again, that's going to be a solid. And then for gaseous carbon dioxide, value should be negative 394.4 kilojoules per mole. Okay, so popping those into our equation, delta G of the standard state reaction is equal to the sum of all the delta G of formation of the products minus the sum of the delta G of reactants. Okay, so that's going to be we'll take the value, the formation value for calcium oxide, which is negative 603.3 kilojoules per mole, plus the value for carbon dioxide, negative 394.4 kilojoules per mole, okay, minus the value for delta G of formation of calcium oxide, calcium carbonate, which is negative 1129.1 kilojoules per mole. All right. All right, so if we take negative 603.3, subtract 394.4 from it, and then subtract a negative 1129.1 kilojoules per mole, we should get for the delta G of the reaction at standard state, we should get a positive 131.4 kilojoules per mole. Okay, so what does this mean? All right, so what this means for us is that the way that we calculated the delta G of the reaction is going to be non-spontaneous in the forward direction. Okay, and again, because of that positive value, that's how we know that value. All right. So we've got delta G of that reaction. Now, there is a way that we could calculate. Delta G straightforward. Okay. So we got the answer that we want. There's another way of calculating delta G. Remember in the last problem, we solved for delta H of the reaction, and that delta H of the reaction was a positive 179.2 kilojoules per mole. Now, in the first problem that we did, we also solved for the entropy of the reaction at standard state, and that was a positive 160 joules per k-mole. Now, we could have used the equation delta G standard state is equal to delta H standard state minus T delta S. We know the temperature. We know the change in entropy. We could pop in our values and solve for delta G that way. So let's double check just to make sure that the values come out right. So the enthalpy for the reaction was a positive 179.2 kilojoules per mole. Okay. And then we're going to subtract that from the temperature. Remember, the temperature is going to be 298 K, and we got to use Kelvin, okay, because the entropy is also going to be in Kelvin. So that's going to be joules per K mole. So that's going to give you 160. Oops, I'm writing 106. Let me erase that. 160 joules per K mole. Now, there is a problem. We got joules. Enthalpies in kilojoules, so we got to multiply, we got to convert joules to kilojoules. So if we take this value and divide by 1,000 joules per 1 kilojoule, we'll get it. All right, so if you take 179.2, and if we go back to the entropy, 160 divided by 1,000, so it's going to be 0.160 times 298, and take that product, and that's going to be subtracted from 179.2. It should give you positive 131.52. And so it's still going to be kilojoules per mole. And our answer is pretty close. I mean, we're off by 1/10 of a kilojoule, so that's pretty good. So that's going to, again, be non-spontaneous in the forward direction. Okay. All right, so we're good. So again, part B, we know this reaction is going to be non-spontaneous in the forward direction. All right, now part C. Here's our problem. We want to know at what temperature does this reaction become spontaneous. So that means we're going to take our equation that we just dealt with, delta G equals delta H minus T delta S, and we're going to say that we're at equilibrium. Because at equilibrium, delta G is going to be 0. And so what we want to know is at what temperature does this crossover occur? All right. So we're going to solve. We're going to take delta H. We're going to take this T delta S part and move it over to the right-hand side. So that way delta H is by itself. So that way we get delta H is equal to T delta S. Now I'm going to solve for temperature, so I'm going to divide both sides by delta S. So temperature is equal to delta H over delta S. Now we have those values. So delta H is going to be a positive 179.2 kilojoules per mole. Delta S, according to what we have over here, it's going to be 0.160 kilojoules per K mole. And so this is going to give us about 1120 Kelvin. So about 847 degrees Celsius, we're going to hit that equilibrium. So that means at if this is the temperature, 1120 Kelvin, if this is the temperature that we're at equilibrium, then that means at 1121 degrees Kelvin, that's when this reaction becomes spontaneous. Okay, so we just figured out at what temperature does that changeover occur. Okay, so now that we've done a delta G calculation, we've calculated delta H, we've calculated delta S, there's got to be a combination of delta H and delta S that makes delta G be favorable or unfavorable. So let's try to see this. All right, so in order to predict the sign of delta G, we need the signs of delta H and delta S for the process. So summarize the various combinations of signs. So here's what we know, okay? There's a combination that will actually tell us if delta G is going to be favorable or unfavorable at all temperatures. So we know this, that if delta H, because delta H is the biggest term, if delta H is greater than 0, so that means it's positive, okay? So that means delta H is unfavorable because it's endothermic, okay? Now, if delta S is negative, so delta S is less than 0, so that also is unfavorable, okay? Delta G will be greater than 0, and so that will also be unfavorable. Now, with those combinations, delta H and being positive and delta S being negative, delta G is going to be positive, and no matter what values you have for delta H and delta S, no matter what temperature you have it at, you're always going to have a positive delta G. So at all temps, okay, at all temps, when delta H is greater than 0 and delta S is less than 0, delta G is always going to be greater than 0 and is always going to be unfavorable. Now, if we go the opposite way, delta H is less than 0, so it's favorable. Okay, and delta S is greater than 0, so that also is favorable. Delta G will be less than 0, so it's going to be negative, which means it's going to be favorable. Okay, and this will work at all temps. Okay, so we've got two possibilities. If, let's say, everything is favorable, if delta H is less than 0, so it's favorable, and delta S is greater than 0, so that is also favorable, delta G is going to be less than 0, which means it's going to be favorable. Doesn't matter the combination, doesn't matter the temperature, it's always going to be that way. Now, here's the problem, though. If delta H is greater than 0, so we know it's unfavorable, okay? And let's say delta S is greater than 0, so that is also favorable, okay? Delta G could be less than or equal to 0, so it could also be favorable under these conditions, but we don't know at what temperatures that is a possibility. Same thing, if we said, let's say the enthalpy is favorable, so it's less than 0, okay? Delta S this time is going to be less than 0, so it's unfavorable. Delta G could be less than or equal to 0, so it could be favorable under those conditions, but we got to specify at what temperatures. Okay? And so this chart, what we just did, we can sum up right here. So it's going to actually tell us this combination. So look, we said if it's unfavorable, if delta H is unfavorable and delta S is negative where it's unfavorable, it's going to be non-spontaneous at both temperatures. So what if we have this where delta H is favorable and delta S is negative, so it's unfavorable? It could be plus, or delta G could be plus or minus. And so now we got to figure out at what temperatures. So it looks like it's going to be spontaneous at low temperatures when delta H outweighs the T delta S, and it's going to be non-spontaneous at high temperatures when T delta S is bigger than delta H. And same thing, if let's say the delta H is unfavorable and delta S is favorable, same deal with delta G. It could be favorable, could be unfavorable, but it all depends on the values of T delta S versus delta H. Okay? All right, so for the two combinations that depend on temperature, what will determine the value of T? So remember that delta G is going to be equal to delta H minus T delta S. Okay, so let's say delta H is positive, so it's going to be unfavorable. Okay, and delta S is going to be favorable, so we'll make that positive. Okay. Now, delta G, in that situation, delta G will be less than 0 if the temperature is high. And so we want T delta S to be bigger than delta H. That's the only way that works. All right. Now, if we go the opposite way, let's say delta H is negative, so it's favorable. And then delta H is going to be negative, so it's going to be unfavorable. Okay. In that situation, delta G will be less than 0 if the temperature is low. So we want in this case, we want delta H to be bigger than T delta S. All right. Now, if you notice, the way I wrote that equation, delta G, I didn't use the standard state symbol. So there's a difference here. There's a difference between delta G and delta G naught. Okay, so delta G naught, this indicates that we're at standard state. So that means we're at 298 K and that we're at 1 atmosphere. Okay, if it's normal delta G, that's the delta G right now. So it's non-standard state. You might be asking, well, who cares? What's the big difference? Well, that big difference is actually what we're going to talk about next. So there's got to be a way to relate the delta G at the standard state with delta G right now, and then tie in equilibrium to that mixture. And that's where we're going next.